Okay. So in the last class, we started our discussion of non-Cartesian tensors. Non-Cartesian Cartesian tensors. Okay. Yeah. So we took an example of a spherical coordinate system, and we saw that the differential of the coordinates, they satisfy an equation like this: dxi prime is equal to dou xi prime by dou xj dxj. Okay. So this dxj on the right hand side, this is the differential of the coordinate in the unprimed system, and this dxi prime, this is the differential of the coordinate in the prime system. Okay. And then we also saw how the partial derivatives of a function transform under a general coordinate transformation. So the transformation equation was dou u by dou xi prime. Okay, here u is a function of the coordinates, and this dou u by dou xi prime, this is the partial derivative of the function u with respect to the prime coordinates, and this is equal to dou xj by dou xi sorry, prime, this is dou xi prime, and dou u by dou xj. Okay, so the second equation shows how the partial derivatives of a function u transform under the coordinate transformation, and the first equation shows how the differentials of the coordinate, they transform under a coordinate transformation. It's a general coordinate transformation, not necessarily restricted to Cartesian coordinates. Okay, so if we compare these two equations, okay, with the transformation of a Cartesian vector. So let us compare these two equations with the with the transformation of a Cartesian vector. That is, suppose I have a Cartesian vector v, then the components of this Cartesian vector vi, they transform under a coordinate transformation according to this rule aij vj. This is the transformation equation for a Cartesian vector. Here aij is the direction cosines of of the angle between the axis xi and xj, sorry, xi prime and xj. So this is the transformation coordinate of a Cartesian vector, and this is how the coordinate differentials transform under a general transformation, and this is how the components of the partial derivatives, or in short, the partial derivatives of a function u transform under a general coordinate transformation. Okay, and then if we look at these two equations from the point of view of a Cartesian vector, that is, for Cartesian vectors, we can easily verify that this dou xi prime by dou xj and dou xj by dou xi prime, these two are the same. Okay, so for a Cartesian vectors, we can easily verify that dou xi prime by dou xj, this is equal to dou xj by dou xi prime, and this is equal to aij for Cartesian vectors. Okay, because both these derivatives, they are simply equal to the cosine of the angle between the xi prime axis and the xj axis. Okay, so both these derivatives, they have the same value in Cartesian vectors. Okay. We can also very easily see how this is achieved. Say, for example, uh, let us recall how a Cartesian vector transform. I repeat, let us recall how a Cartesian vector transform. If you remember this xi prime is equal to aij xj. This is how the coordinates transform from the unprime frame to the prime frame when we consider the rotation of a Cartesian coordinate system. So let me draw it here. I have a Cartesian coordinate system. Here we have x, I have y, I have z, x, y, z. And let me change the color a bit. So I rotate the coordinates to x prime, y prime, and z prime. Okay, then I take any point. I take any point here. So let me take any point here. I take any point here P. The coordinates of the point P in the XYZ frame and the coordinates of the point P in the X prime, Y prime, Z prime frame, these two coordinates are related by this equation. Okay, and here Aij is actually the cosine of the angle between the xi prime axis and xj axis. Okay, so here I can write xi, the unprime coordinate, in terms of the prime coordinate. Then we'll get aji xj prime. Okay, so this is the prime coordinates in terms of the unprime coordinates. I invert this equation and I obtain the unprime coordinates in terms of the prime coordinates. Okay, now if I interchange I and j in this second equation, so if I interchange I and j here, what do I get? xj is equal to a ij xi prime. Okay, so for this particular coordinate transformation, let me use the spotlight now. So for this particular coordinate transformation, xi's are expressed in terms of xj here. That is the prime coordinates of the point P are expressed in terms of the unprime coordinates. We can invert this equation and we can express the unprime coordinates in terms of the prime coordinates here. Okay, so we can use this equation and calculate these two partial derivatives. Okay, so let us calculate these two partial derivatives. So from this first equation, let us calculate the first partial derivative. Okay, so let me use another. So yes, so this first partial derivative, let us calculate it here. So what do we have here? Dou xi prime by dou xj. Dou xi prime by dou xj. Now, if I look at this equation, I see that dou xi prime by dou xj is nothing but aij. So it is aij. So this is aij. Okay. Now let us look at the second partial derivative, dou xj by dou xi prime. Dou xj by dou xi prime. To calculate this second partial derivative, we shall use this equation. Okay, so from this equation we have dou xj divided by dou xi prime is equal to aij. So we see that from these two equations, we see that dou xi prime by dou xj and dou xj prime by dou xj by dou xi prime, they have the same value. So for a Cartesian vector, this expression, and this expression, they have the same values. Okay, but this is not true for general coordinate systems. For example, if we transform from the Cartesian coordinate system to the spherical polar coordinate system, then we can easily see that these two are not the same. So let us look at that. So let us look at a simple example. Okay, so let me do it on the side here. I'll use a different color. Okay, so now we want to show that for an arbitrary coordinate transformation, those two partial differentials, they are not equal. So for simplicity, let us take a two-dimensional case. Okay, so let me draw here. Let me draw a case here. Sorry. Let me make the drawing here. I have this and I have that. This is a point in the two-dimensional plane P. This is my x-axis. This is my y-axis. And this is my origin. Okay, point P, x-axis, y-axis, and my origin. Now let us consider the transformation between rectangular coordinates and polar coordinates in a plane. So the polar coordinates is given by, this is r, and this angle is theta. So what is the relation between the rectangular coordinates and the polar coordinates in a two-dimensional plane? The relation is, let me use a different color. The relation is given by x equal to r cos theta, y equal to r sin theta. So this is the relation between x, y, and r theta. Okay. So this gives us r equal to root over x square plus y square, and theta equal to tan inverse y by x. Okay. Then suppose we want to find this dou theta by dou x. Okay, suppose we want to find dou theta by dou x. Then we can find this dou theta by dou x from this expression. So this would be dou by dou x of tan inverse y by x. This is tan inverse y by x. So when we calculate dou theta by dou x, we are actually keeping y constant. Okay, so in this calculation, we are actually keeping y as a constant. So this should be equal to, so first let us calculate the differential of tan theta. Okay, so we should get 1 plus y square by x square, and then we differentiate y by x part. That should give us minus y by x square. Now if I multiply by x square in both the numerator and the denominator, what should I get? I should get minus y by r square. Okay, so this is the value of dou theta by dou x at constant y. This is the value. Okay, so far so good. Next, let us calculate dou x by dou theta. So next, let us calculate dou x by dou theta. Let me use a different color to make the distinction clear. Now we are going to calculate dou x by dou theta. That means we are differentiating x with respect to theta, keeping r constant. Now to calculate this, what do? We actually use this relation. Okay. So dou x by dou theta is the differentiation of r cos theta, keeping r constant. So this will be minus r sine theta. And what is minus r sine theta? R sine theta is y. Therefore, minus r sine theta is nothing but minus y. Okay. So what have we seen here? We have seen that dou theta by dou x and dou x by dou theta. Mathakta sidana theta lere, sidana x lere, aduga somdana mathakta x lere, makada theta lere. Sigi anisi amana amagi reciprocal gani ne koi hana kalambiya. But no, it actually turns out that this and this, they are not reciprocals of each other. They are totally different functions. Here we have minus y, and here we have minus y by r square. So dou theta by dou x at constant y and dou x by dou theta at constant r, we find that these two are not the same. For a transformation of coordinates from Cartesian coordinate to polar coordinates. I repeat, so for transformation of coordinates from the Cartesian coordinates to polar coordinates, these two values are not the same. So if we refer to our earlier slide, we see that this was actually dou theta by dou x, and this was dou x by dou theta. Okay, so these two are not the same for coordinate transformations from Cartesian coordinate system to polar coordinate system. However, if we consider only transformation of one Cartesian coordinate system to another Cartesian coordinate system, these two actually turn out to be the same. So for transformations corresponding to Cartesian vectors, these two are the same, but for transformations corresponding to general tensors, these two are not the same. Thus, in general, we have two possible definitions of a vector. And these two possible definitions, they become identical for Cartesian vectors, but they are not identical for general non-Cartesian vectors.